Hello dear students, today we'll study the next point, that is Thyristor controlled series capacitor TCSC. So this is the configuration of series controller. Earlier we have covered static or compensator, and the configurations or the controller which comes under FVCs were FCTCR, TSCTCR and STATCOM. All these controllers are nothing but your shunt controllers. Today we'll start with the next, that is series controllers, and one of the important controller is Thyristor controlled series capacitor TCSC. So figure shows the basic diagram of Thyristor controlled series capacitor. The basic conceptual TCSC module comprises of series capacitor in parallel with Thyristor controlled reactor L. So the capacitor is connected in series with the line, and the thyristors are connected back to back. Connected thyristors are connected in parallel with that capacitors. So it is represented by L and C, that is thyristors are represented by the inductance L and the capacitor is represented by C. A TCSC is a series controlled capacitive reactance that can provide continuous control of power on AC line over wire range. From system point of view, the principle of variable series compensation is simply to increase the fundamental frequency voltage across fixed capacitor in series compensated line through appropriate variation of the firing angle alpha. This enhances the voltage changes the effective value of series capacitive reactance. So by just controlling the voltage across the capacitor, by controlling the firing angle of thyristors, we are going to control the reactive compensation. That is nothing but this capacitor or series capacitor's voltage mainly depends upon the firing angle of back-to-back connected thyristor, which is connected in parallel with the series capacitor. So the figure 1, where we have shown a capacitor connected in series and back-to-back thyristors connected in parallel with the series capacitors, that means it is simply LC branch or LC network. So the simplified diagram of figure number 1 is shown in this figure number 2. The impedance of LC, so from this figure, the impedance of LC network is given by, now we have two impedances over here, capacitive impedance and inductive impedance. So we'll need to calculate the effective impedance or equivalent impedance of this circuit. So that is nothing but equivalent impedance, Z equivalent is equal to XC is nothing but reactance of capacitance into XL, that is nothing but reactance of inductance or back-to-back connected thyristor volts, divided by XC plus XL. So we have the equivalent impedance equation as Z equivalent is equal to XC into XL divided by XC plus XL. Now we have three conditions over, or two conditions over, when the omega L is greater than 1 upon omega C, or simply I will say that the inductive reactance is greater than capacitive reactance. The reactance of Fc, that is fixed capacitor, is less than the parallel connected variable reactance or back-to-back connected reactors, and this combination provides variable capacitive reactance are both implied. Moreover, this inductor increases the equivalent capacitive reactance of the LC combination above that of Fc, that is fixed capacitor. If omega C minus 1 upon omega L is equal to 0, that is nothing but when capacitive reactance is equal to inductive reactance, a resonance is developed, or the net reactance is equal to 0, that is X is equal to 0, Then we have the resonance condition. So resonance is developed that results in infinite capacity impedance and obviously unacceptable condition. So this condition is highly not acceptable because if the resonance condition occurs, there will be oscillations present in the system, and since it is in series, so the impedance will of the line will get increased, and if the impedance get increases, there will be large voltage variation across the load end, and thus this controller will not able to compensate this voltage variation. So we need to avoid this resonance condition in the system. If omega L is less than 1 upon omega C, the LC combination provides inductance above the value of fixed inductor. This situation corresponds to inductive Vernier mode of the TCSC. Inductive Vernier mode. That means inductive. This is one of the method of controlling TCSC. That is inductive Vernier mode. We will discuss further this mode in detail. So in first case, that is when omega L was greater than 1 upon omega L, 1 upon omega C, that time the capacitive inductance was high. But here, in case of omega L less than 1 upon omega C, here inductive reactance will get increased. That means the TCSC controller will mainly depend upon the inductive reactance. Hence, the name is given as inductive Vernier mode of TCSC operation. In variable capacitance mode of TCSC, as inductive reactance of variable inductors is increased, the equivalent capacitive reactance is gradually decreased. The minimum equivalent capacitive reactance is obtained for extremely large inductive reactance or when the variable inductor is open circuited, in which the value is equal to reactance of Fc itself. The behavior of TCSC is similar to that of parallel LC combination. So this is one of the mode of TCFC operation. We have three different modes we are going to discuss in details. The difference is that LC combination analysis is based on the presence of pure sinusoidal voltage and current in the circuit, whereas in TCSC, because of voltage and current in FC, thyristor controlled reactor are not sinusoidal because of thyristor switching. In case of fixed capacitor, we are able to get sinusoidal waveform, but in case of TCSC, due to switching of thyristors, it is highly impossible to have sinusoidal voltage or sinusoidal waveform. So modes of operation of TCSC. So there are three different modes: bypass thyristor mode, block thyristor mode, and partially conducting thyristor or Vernier mode. This is nothing but inductive Vernier mode. So first mode is bypassed thyristor mode. So this is the diagram for the arrow shows the direction of voltage and current in this bypass thyristor mode. In bypass thyristor mode, the thyristors are made fully conduct with conduction angle of 180 degree. Gate pulses are applied as soon as the voltage across the thyristors reaches zero and becomes positive, resulting into sinusoidal flow of current through the thyristors wall. So this is shown from the waveform shows the direction of current, that is from source through thyristors wall. Here the thyristors are given the gate pulses. As as soon as the gate pulses are given, it becomes it goes in on condition, and due to which the current flows from source to load through this parallel thyristor branch, and from load back to source. So where it is shown by the arrow over here. The TCSC module behaves like parallel capacitor inductor combination. However, the net current through the module is inductive. for the susceptance of reactor is chosen to be greater than capacitor. So the susceptance of reactors is greater than capacitor in case of bypass method. That means it is highly inductive, or this mode is highly inductive. Also known as thyristor switch reactor mode (TSR), the bypass thyristor mode is distinct from bypass breaker mode, in which circuit breaker provides across series capacitor is closed to remove the capacitor or TCSC module in the event of TCSC faults or transit over voltage across the TCSC. So the point to be concluded in this bypass method is whatever the current will flow is mainly dependent upon the conduction angle applied across the thyristor wall. That is when we apply the firing angle to the thyristor wall, and when it goes into conducting mode, or it becomes positive. So the current will flow from this parallel thyristor wall to the load. That means the current which will be flowing in the circuit or line will be highly inductive in nature. This mode is employed for control purpose and also for initiating certain protective functions. Whenever TCSC module is bypassed from violation of current limit, a finite time delay, that is T delay, must elapse before the module can restrain after the line current falls below the specified limit. So if there is miss switching of the thyristor's wall, or when the TCSC module is bypassed, there should be some time delay in order to restore the system. So there should be a finite time delay which is represented by T delay in order to restrain the line current when it falls below the certain limit. So this was about the bypass mode. Now second mode is block thyristor mode. So this is the diagram of block thyristor mode. In this mode, also known as waiting mode, the firing pulses of thyristor walls are blocked. If the thyristors are conducting and a blocking command is given, thyristor turn off as soon as the current through them reaches zero crossing. The TCSC module is thus reduced to fixed series capacitor and net TCSC reactance is capacitive. In this mode, the DC offset voltage of capacitor are monitored and quickly discharged using DC offset control without causing any harm to transmission system transformer. So in this mode, so the bypass mode, what we have done, we have bypassed the current through the thyristor wall directly. Uh, Despite of passing the current through series capacitor, it was bypassed through the thyristor wall. That means the current was completely in control of the thyristors. But in case of block thyristor mode, the thyristors are in off condition. So whatever the current will flow through the system will directly flow through the series capacitor connected in the line. That means this current will be completely dependent upon the fixed current value, that is nothing but voltage of series capacitors. And this voltage of series capacitor is controlled by using DC offset voltage. By controlling this DC offset voltage, we can control the amount of voltage and current without any disturbances in the transformer. So third method is partially conducting thyristor or Vernier mode. So partially method is nothing but there will be a fixed capacitor mode also and thyristor mode also. So first mode was completely dependent on thyristor. Second mode was completely dependent on fixed, and the third method fixed capacitor, and the third method is the name itself gives it's partially. That means the thyristor will be partially on and partially off. That means the control of current will be both for fixed capacitor and thyristors. So figure shows the operation of this partially conducting thyristors or Vernier mode. This mode allows TCSC to behave either as continuously controllable capacitive reactance or continuously controllable inductive reactance. It is achieved by varying thyristor pair firing angle in appropriate range. So we have two modes over here. that is capacitive mode and inductive mode, and this can be obtained or it is achievable just by controlling the conduction of firing angle of the thyristor wall in appropriate range. However, smooth transition from capacitive to inductive mode is not permitted because of resonant region between two modes. Now the main problem of this type of mode is nothing but resonance, because we are going to switch from capacitive mode to inductive mode. So there is might be possible that the reactance of these both might become equal, and we have already studied that when the resonant condition occurs, the impedance get increases, and if the impedance get increases, there will be a lot of voltage variation across the load end side. So the one of the drawback of this mode is nothing but there is not smooth transition between capacitive mode and inductive mode. A variant of this mode is capacitive Vernier control mode, in which the thyristors are fixed when capacitor voltage and capacitor current have opposite polarity. This condition causes TCR current that has direction opposite to that of capacitor current, thereby resulting loop current flow in TCSC controller. The loop current increases the voltage across fixed capacitor. That means in this, the current of capacitor and the current of inductor will be in opposite direction. That is nothing but in case of capacitive Vernier control mode, the capacitive current and inductive current will be opposite to each other. So at that time, the voltage across the fixed capacitor will be high. The loop current increases the voltage across fixed capacitor, effectively enhancing the equivalent capacitive reactance and a series compensation level of same of the line current. So we have seen that when the voltage across capacitor get increases, that means the capacitive reactance will be also high, and if the capacitive reactance is high, it reduces the impedance of that line, and if the impedance of that line is reduced, that means the voltage variation also will be get reduced. To preclude resonance, the firing angle alpha of forward facing thyristor, as measured from positive reaching a zero crossing of the capacitor voltage, is constrained in the range alpha minimum greater or equal to alpha less than or equal to alpha maximum. This constraint provides a continuous Vernier control of TCSC module reactance. The loop current increases as alpha decreases from 180 degree. So it is raised to, it has become wrongly written as 1800. So it is 180 degree, make it correct, to alpha minimum. The maximum TCSC reactance permissible with alpha is equal to alpha minimum is typically 2.5 to 3 times the capacitor reactance of fundamental frequency. Another variant is inductive Vernier mode, in which TCSC can be operated by having high value of thyristor conduction. In this mode, the direction of circulating current is reversed and the controller presents a net inductive impedance. So in case of inductive Vernier mode, the conduction of thyristor will be high and the net impedance will be nothing but inductive impedance, whereas in case of capacitive Vernier mode, the net impedance will be capacitive impedance. Based on three modes of thyristor wall operation, two variants of the TCSC emerges: thyristor switch series capacitor, which permits a decreased control of capacitive reactance; thyristor control series capacitor, which offers continuous control mode of capacitive or inductive reactance. That the TSSC, however, is more commonly employed. So depending upon the control of capacitor and inductance, we have two modes. That is mainly the first mode is mainly capacitive reactance mode, and second mode is nothing but shifting of capacitive mode to inductive mode, or from inductive mode to capacitive mode. That is nothing but capacitive or inductive reactance mode. So this is analysis of TCSC, we'll get lot of equations over here. Just we have to uh, have brief look over here. We are not interested to how these derivations are derived, but we'll directly see the equations over here. So this is the diagram, equivalent diagram of figure number one. That is, we have capacitor in series and the parallel inductive branch over here. So analysis of TCSC operation in Vernier control mode is performed based on simplified TCSC circuit. The transmission line is assumed to be independent input variable and is modeled as an external current source I of ST, IST, IS of T. It is further assumed that the line current is sinusoidal as derived from actual measurement, demonstrating that very few harmonics exist in line current. However, the analysis present in the following text may be erroneous to extend that the line current deviates from purely sinusoidal nature. So, whatever the equation we are going to study in this is derived by some assumption, that is nothing but whatever the current source which we are used over here, we are assuming that this current source is sinusoidal in nature. But practically, this might be not the case. That is nothing but the current source may have some harmonics present in it. So the current through the fixed series capacitor, which is connected in series, is expressed by C dVc by dt is equal to I st minus I t of t into u. The switching variable u is equal to 1 when the thyristor volts are conducting. That is, when switch S is closed. On the other hand, u is equal to 0 when thyristors are blocked. That is nothing but when switch is open. So whatever the current that flows to the capacitor flows when the thyristor is in on condition. So that is nothing but the parallel branches also attached to the circuit. That is nothing but the current will flow from first from source, that is I s of t, to the thyristors wall, that is which are conducting or which is positive, from conductor to the secondary side of the transmission line, and from transmission line to the series capacitor. That is nothing but from source to load, that is from source to thyristor wall, from thyristor walls to secondary side of the transmission line, that is nothing but if you consider a load, and from load to the source, that is nothing but from load to the source there is a line, and in that line we have connected a series capacitor. That means the current will also flow through this series capacitor, and at this condition, and in this condition, the value of capacitor voltage developed is given by equation C into dVc by dt is equal to I s into t minus I t of t. That is nothing but the direction of source current and capacitor and the current flowing through the thyristor wall is opposite. So we have difference of these two currents. The thyristor wall current it of t is then described by, so since the thyristor is nothing but it is inductive in nature, so the current is given by L dit by dt is equal to Vc into U. Let the line current Is of t be represented by, since we have considered this source current as a sinusoidal, so that means this current will have sinusoidal equation, that is nothing but Im cos omega t. So Is of t is equal to Im cos omega t. So above equation can be solved with knowledge of instant of switching in equidistant firing pulse control. For balanced TCSC operation, thyristors are switched on twice in a cycle of line current at instant T1 and T3 given by. So what this equation indicates, or what this line indicates, so we have studied that in this TCSC there should be no generation of resonance. If the resonance in condition occurs, then the impedance will get increased, but we have to reduce this impedance. So in order to avoid this resonance condition, we have to control the thyristor switching in such a way that The capacitive reactance Xc and inductive reactance XL should not become equal, and this is mainly controlled by controlling the firing angle of thyristors. So it is given as the TCSC operator. The thyristors are switched on twice in a cycle of line current at instant T1 and T3, given by T1 is equal to minus beta divided by omega, and T3 is equal to pi minus beta divided by omega, where beta is the angle of advance before forward voltage becomes zero. We already know the working of thyristors: forward voltage, backward voltage, conduction, or thyristor switching. How we can do the thyristor switching? That is nothing but if you consider three phase converters, we have six thyristors present, or we have three branch and six thyristors: T1, T2, T3, T4, T5, and T6. And how these thyristors are connected in a single branch, and how the thyristors are switched. That is nothing but in case of three phase, in forward mode, there will be two pairs of thyristors will be in positive direction or forward mode. Then in order to switch the next mode, we have some conductions of the previous pairs of thyristors. So the next pair of thyristors should be turned on before the previous mode or first pair voltage becomes zero. So in this way we can avoid the resonance condition. So where beta is nothing but angle of advance before the forward voltage becomes zero, or beta is equal to pi minus alpha, beta greater than zero and less than beta maximum. The firing angle alpha is generated using reference signal that can be in phase with the capacitor voltage. The thyristor switch S turns off at instant T2 and T4, defined as T2 is equal to T1 plus sigma divided by omega, where sigma is nothing but conduction angle, and T4 is equal to T3 plus sigma divided by omega. So we we have four times mode: T1, T2, T3, and T4. So thyristors will be conducting in conducting mode for time period T1 and T3, and it will be in off mode for the time period T2 and T4. That is nothing but for on odd time period, thyristor will be in conducting mode, and for even time period, thyristor will be in off mode. Where sigma is the conduction angle, which is assumed to be same in both positive and negative cycle of conduction. Also, it is given by sigma is equal to 2 beta, where beta is nothing but for advance angle, that is nothing but when the conduction voltage or the angle before which the conducting voltage becomes zero. Solving TCSC equation results in steady state thyristor current. Here the current flowing through the thyristors is given by equation IT of t is equal to k square divided by k square minus 2 into cos omega t minus cos beta divided by cos k into beta multiplied by cos omega r t, where omega r is nothing but that is reactance of thyristors, that is 1 upon under root LC. This is nothing but resonance conditions or equation for resonance frequency omega r, and k is equal to omega r divided by omega, that is resonance frequency divided by omega or fundamental frequency, which is equal to under root 1 upon omega L into 1 upon omega C is equal to under root xc divided by xl, and xc is nominal reactance of fc only. So do you I think everybody knows the q factor. What is q factor? It is nothing but xc divided by xl or xl divided by xc. So this q factor is mainly dependent upon the resonance condition. The steady state capacitor voltage at the instant of omega t is equal to minus beta is given by Vc1 is equal to Im into xc divided by k square minus 1 sin beta minus k cos beta into tan k beta. At omega t is equal to beta, the thyristor current is equal to 0, and the capacitor voltage is given by Vc of omega t is equal to beta is equal to Vc2 minus Vc1. The capacitor voltage is finally obtained as Vc of t is equal to Im Xc divided by k square minus 1 into sine omega t plus k cos beta divided by cos k beta into sine omega rt. So therefore, if we substitute, we get Vc of t is equal to Vc2 plus Im Xc sine omega t minus sine beta. Because the non-sinusoidal capacitor voltage has odd symmetry about the axis omega t is equal to 0, the fundamental of capacitive current or capacitive voltage obtained or fixed capacitor voltage obtained is Vcf is equal to 4 divided by pi integration 0 to pi by 2 Vc of t sin omega t into dt d omega t, and the reactance of TCSC, that is considering the thyristors and capacitor, is given by x TCSC is equal to Vcf divided by Im. X TCSC is equal to Vcf divided by Im is equal to Xc minus Xc square divided by Xc minus XL 2 beta plus sine 2 beta divided by pi plus 4 Xc square divided by Xc minus XL into cos square beta divided by k square minus 1 into k tan k beta minus tan beta divided by pi. So I think these equations are very much difficult to understand. I know. So generally, what they have done in these equations, that is, whatever the voltage will be generated across the capacitor will be mainly dependent upon the thyristors, and we know that there will be occurring of resonance conditions if we have the Vernier mode, that is nothing but capacitive Vernier mode or inductive Vernier mode, or by switching the capacitive Vernier mode to inductive Vernier mode. That means the all the current, that is, or the reactance will be mainly dependent upon the thyristors. So in order to avoid the resonance condition, what we have done, we have uh, turn on the thyristors in odd time, that is nothing but T1 and T3, and we are going to turn off the thyristors for even time, that is nothing but T2 and T4. So we have alpha and beta angles, that are nothing but conduction angles. So in conduction mode, if you control the conduction mode, indirectly we are going to control the turning on and turning off of the thyristor, and if indirectly by controlling the conduction of thyristors, we are controlling the current flowing through the capacitor. That means whatever the capacitor voltage will be developed will be directly dependent upon the thyristor conduction mode. So all these equations mainly gives this brief idea. So the advantage of TCSC: rapid continuous control of transmission line, series compensation level. So the compensation will be higher, that is nothing but since we have inductive compensation or inductive reactance and capacitive reactance present in the system. So the since we have two mode, that is nothing but capacitive Vernier mode and inductive Vernier mode, that means the compensation will be high, or the level of the compensation will be high. Dynamic control of power flow is selected in selected transmission lines within the network to enable power flow condition and prevent the loop flow of power. Since we have the control of inductive and capacitive, so there will be a dynamic power flow in the system or selected transmission line. Damping of power swings from local and inter-area oscillations. So we are going to damp out the oscillation damping is more in case of TCSC. Suppression of subsynchronous oscillation at subsynchronous frequencies. The TCSC presents an inherently resistive inductive reactance. The subsynchronous oscillation cannot be sustained in this situation and consequently get damped out. Decreasing DC offset voltages, since we have know that in case of FC mode, the series reactance will be high. That means the voltage of the capacitor will be high. So we need to control this capacitor voltage by DC offset voltage. So we have the control over the DC offset voltage, and thus we have the control over the reactance of series capacitor. So the DC offset voltage invariably resulting from insertion of series capacitor can be made to decay very quickly within few cycles from firing control of TCSC thyristor. That means this DC offset voltage will be controlled by controlling the firing of thyristors. If we plot the waveform for a fixed capacitor, we'll have a sudden shoot in the capacitor voltage, but by controlling the thyristors, we can decrease this shooting of the capacitors, and that means the voltage across the capacitor will decrease in decaying manner. Enhanced level of protection for series capacitors. A fast bypass of series capacitor can be achieved through thyristor control when large overvoltage develops across the capacitor following faults. Likewise, the capacitor can be quickly reinserted by thyristor action after the fault clearing to aid in the system stabilization. Voltage support. The TCSC in conjunction with series capacitor can generate reactive power that increase the line loading, thereby aiding the regulation of local network voltage and in addition the elevations of any voltage instability. And the last advantage is reduction of short circuit current. During event of high short circuit current, TCSC can switch from controllable capacitance to controllable induction mode, thereby restricting the short circuit currents. So this is one of the advantage of TCSC. So up till now we have covered a shunt type controller, that is nothing but description of SVC, then FCTCR, then TSC-TCR, then switching mode, that is nothing but statcon or statcom. So also you will find a word statcon in your syllabus, that is nothing but it represents the generally static compensator or statcom. And then today we have started with series controllers, and the first controller is TCSC. Then in next lecture we are going to study S3C, that is nothing but static series synchronous compensator, that is S3C. And after that we are going to cover the combined controller, that is nothing but UPFC, that is unified power flow controller. So this is for today's lecture. Thank you for listening, and if you feel you have any doubts regarding this, you are free to call me or message me. Thank you.